Hello guys, this is Muhammad Tajuddin from group number 324. Today I am explaining two chapters from biophysics written by M.V. Wolkenstein. So in this video I am going to explain about double helix DNA bond formation, Gibbs free energy, change in enthalpy and change in temperature, etc. So let us start. The structure of double helix of DNA or double stranded DNA determined by the weak interaction, hydrogen bonds and electrostatic dispersion forces. In this double helix DNA or double stranded RNA, there are free nitrogen bases form the hydrogen bond. There have been some structure differs from the Crick-Watson model of DNA. The double helix coiled structure is proposed by Watson and Crick. So there are some structure differs from that. For example, this structure in this photo you have seen the structure which is 9-methyl adenine 1-methyl thymine. In this structure, the N1 of thymine and N9 of adenine are blocked by methyl group to avoid hydrogen bond formation. So there is no interaction between N1 of thymine and N9 of adenine. Actually, adenine forms hydrogen bond with thymine, but in this methyl blocks that bond in N1 region of thymine and N9 region of adenine. So for the mutagenesis, for the formation of mutation, tautomerism and new hydrogen bond formation is needed. For example, when bromouracil is a strong mutagen is examined with ethyl adenine and methyl adenine, two different structures are obtained. In ethyl adenine, the hydrogen bond is formed between O2 and N6, N3 and N7, where in methyl adenine O4, N6 and N3, N2. So when the strong mutagen bromouracil is examined from two structures, two different structures are formed. So it is remarkable that the hydrogen bond formation only between adenine uracil, adenine thymine, guanine cytosine, but not in adenine cytosine or guanine thymine, guanine uracil or adenine guanine. There should be a formation between only adenine thymine, adenine uracil in RNA and guanine cytosine. The melting point of double helix depends on the linear content of hydrogen bond pairs. So hydrogen bond is formed between the horizontal interaction. So there are also the stacking interaction between double helix in the neighboring bases. So hydrogen bond is formed in the double helix. Hydrogen bond is formed as a horizontal interaction, but there are also between the neighboring base pairs there is a stacking interaction. In nitrogen or pi electronic system, so there is a strong dispersion interaction occurs between planar pi electrons. For example, in this figure, the structure of polynucleotide region of double helix coil transition are explained. So that's all about the hydrogen bond between double helix DNA coil or the double stranded RNA. Now, and I also explain another small topic which is the thermodynamics in the double helix. So what is thermodynamics? Thermodynamics is the study of energy, how energy transferred, how energy maintained in the body or in the system. So in nucleic acids such as DNA, RNA, denaturation of nucleic acid boils down to destruction of double helix or double stranded double stranded RNA. In this denaturation, viscosity and optical activity are diminished. So, the melting point of DNA is studied by Doty in 1957. So far, free energy discussion. You know that in thermodynamics it is a main topic about Gibbs free energy. In this Gibbs free energy, we give disrupted pairs as N1 and bond pairs as N2, and smaller n is equal to number of loops in this coil. So G is equal to, and Gibbs free energy G is equal to N1G1 plus N2G2 plus NGS minus TS0, where G1 and G2 are Gibbs free energy, S is entropy, and T is temperature. So for S, for entropy, we need R natural log N1 factorial divided by small n factorial into N1 minus n factorial into N2 factorial by n factorial into N2 minus N1 whole factorial. In this equation we can find entropy. So the minimum Gibbs free energy at particular given temperatures we can easily measure it by N1 by n minus 1 into N2 by n minus 1 is equal to 1 minus sigma, where sigma is equal to exponential to the power minus g divided by RT. Where sigma is lower, there is a higher cooperativity between the double helix. In this, for equilibrium condition, it's a difference between, we can measure the equilibrium of the double helix. It's a difference between G1 and G2, that is 1 minus n by n2 divided by 1 minus n by n1, which is equal to S, which is equal to exponential of G1 minus G2 divided by RT. For the minimum temperature change, we need delta T is equal to 1 by d theta by dt. So in this figure 7.13, it's a curve of double helix coil transition in DNA based on the Ising model. In this where delta T is equal to 4 sigma to the power half whole into RT, R temperature maximum square divided by delta enthalpy delta H, where in this from the experimental value we got that value delta T, this is the change in temperature is approximately is equal to 10 to the power minus 4 to 10 to the power minus 5, and Gibbs free energy is approximately is equal to 30 kilojoule per mole. That's all about this double helix thermodynamics and bond formation. Thank you.